Once, during a working day, something extraordinary happened to me. How much longer must I wait? Welcome to the Hilbert Hotel. Could you check me in a bit quicker, please? I've been traveling for 15 hours, with 2 layovers, one of them in India. I'm absolutely exhausted.
I'm afraid I have to disappoint you, but unfortunately, we have no vacancies at our hotel today.
Is this a joke? This is the Hilbert Hotel, isn't it?
Yeah.
Is this your flyer?
Yes.
Well, the Hilbert Hotel. Infinite number of numbers.
Yes, there are an infinite number of rooms.
So how is it possible that in a hotel with an infinite number of rooms, you can't find one more for a single person?
The thing is, right now there are an infinite number of guests staying at the hotel. One infinity has completely filled up another. If you know what I mean.
Wait, but there are 8 billion people on the planet. That's a perfectly finite number. So where did you get an infinite number of people in your hotel from?
We do not disclose information about our guests.
Oh, I see how it is. What a load of rubbish. All right, the complaints book.
Yes, of course. The complaints book. Don't forget to write your full name, the date, and a contact number.
Oh, believe me, I'll do everything properly here. Comrade. What are you doing? I'm filling out a complaint. Is your name Al? Oh. And what are you writing next? And next is my surname. Is your name Al?
No, I'm Al.
Stop. How many more A's and LS are there?
An infinite number. What's surprising? You've got an infinite hotel, I've got an infinite surname.
Which won't fit into a finite complaints book.
And while I'm filling it in, you'll have time to think of a solution.
All right, there's a mathematical trick that will allow us to accommodate you. It says that if you add 1 to infinity, it still remains infinity.
And why couldn't you just add it straight away? I'm tired. It's been a long journey. 2 transfers, 1 in India. Check me in.
Because to do that, I'd have to disturb every single guest, and there are infinitely many of them.
I don't care.
Attention, attention. To all guests, please pack your things right now and move from your current room to the next one. I repeat, from your current room to the next one. We apologize for the inconvenience.
The infinite hotel is not a metaphor, but a thought experiment by the mathematician David Hilbert. The rooms in such a hotel represent what is called countable infinity. You can add 1 to it, but only from the very beginning. Then each current number will shift by 1, so the guest from room 1 will move to room 2, from room 2 to room 3, from room 3 to room 4, and so on endlessly. As a result, the first room will become vacant, and we'll be able to accommodate a new guest in it.
That is, you.
Excellent. Yes, Piotr Sergeyevich. Yes, all's fine. Checked in. Yes, the city has problems, but here there are numbers. Yes. And how many of you are there? Well, yes, I think we'll manage.
Does anyone else want to come?
Yes, is that a problem? It's not a problem anymore.
Depends how many there are.
I'll call you back. The number of my friends knows no bounds. Young man, there are infinitely many of them. You've checked me in, so check in my friends as well. Makes sense, doesn't it? Or is this too much for mathematics to handle?
Mathematics can handle it, but we'll have to move the guests around in a different way.
Well then, go on, check them in.
Attention, attention. All guests, right now, please pack your things, multiply your room number by 2, and move into the room with that number. We apologize for any inconvenience.
So, the guest from room 1 moves to room 2, from room 2 to room 4, from room 3 to room 6, and so on. All of these are even numbers. It turns out that all the odd numbers are freed up. And since there are infinitely many odd-numbered rooms as well, we can accommodate a new infinity of guests in them.
So all your infinite friends will get a room. Problem solved.
How much I love mathematics. Well then, shall I call my friends?
There's one condition.
What is it?
The main thing is that your friends don't have infinitely long surnames. I hope that's the case.
You're joking. Of course not. We're all completely mad, after all. For example, Ilyuka's surname is A, Sergey's surname is Alar, and Petrovich is just.
No. No.
Is that sarcasm?
No. Yes. Well, actually, no.
Well, now you've stumped me. Because now mathematics knows for certain that it's impossible to settle all of you at the same time, 100%.
I don't believe you. You just fit infinite guests into an already infinitely full hotel. What difference does it make if they have infinite surnames or not?
I'll explain.
Go on, explain.
To understand the difference, let's write down the guests' infinite names in a table. We randomly write names using the letters A and L. First, a la, then a lala and the rest of the A's, and so on, endlessly. And now comes the actual mathematical trick. I'll flip the first letter of the first name and write it out separately. If it was a, it becomes L. For the second name, I'll flip the second letter and write that out as well. If you go through the whole list like this, you'll end up writing out a new name. And no matter how many infinite names you add to the list, I will always be able to find a unique name that differs from all the others by at least one letter. And since you have infinitely many friends, this name will definitely be among them. Take your pick. Either I let you in, or all of you, but one of them will always be left outside. And it might be you. That's the mathematics of the situation.
Yen, if you're holding a gun... What the hell is going on here in your hotel? You've got infinite rooms. You could house people forever. So put me up, for fuck's sake. I'm knackered. I want to sleep.
I see your patience has run out. And I understand you. You thought there was only one infinity, that it was something vast and countless. But in fact, there are many infinities, and some of them can be smaller or larger than others. And it's precisely this fact that means you won't be able to check into our hotel tonight.
Oh, really? What if I blow your brains out right now? You're the Grinch, the Christmas thief who's bleached his face an asshole.
Satire, that wasn't in the script. This is an episode about mathematics. Give me your bloody passport. I'll check you in and you can go and get some sleep. Your room is number 1. You can leave your things here. We'll bring them up to your room ourselves. Welcome to Gilbert's Hotel. Today there'll be plenty of mathematics, infinities, thought experiments, and black holes.
Welcome to Gilbert's Hotel.
Now you'll find out which ideas blew scientists' minds and how this whole hotel circus is connected to Einstein. What number comes immediately after 0? Mathematicians, Yoo-hoo, why won't you be able to count all the points in the sky, even if you're paid for it? Why is everyone in the world the same height? Is it possible to peek under the skirt of the visible universe? How can you turn your legs into elegant spaghetti? How can you look inside a black hole? Well, if you know what I mean. Where can you spit on the back of your own head? How can you avoid having a stroke when you see this formula? And of course, what awaits you beyond the event horizon, but not the current one? Welcome to an infinitely fascinating episode. Let's rack up some views for this madhouse.
Jan, how tall are you? Personally, I'm 179. But I can say with confidence that you and I are the same height. Yes. Are you trying to say that you're shorter or taller? Yes, please. That doesn't contradict my statement in the slightest. You and I are the same height. So far. Yes, that sounds like complete nonsense. Yes, I understand, but remember it and keep it in mind. For now, let's figure out what sameness actually means. Look at these two wheels. One is clearly half the size of the other, but let's check the length of their circumference. We roll each one exactly one revolution and the lines turn out to be absolutely identical. What did I say? No matter what size the wheels are, as soon as you join them together in the middle, their circumference becomes the same length. Yes, it's a bit of a paradox. Aristotle's wheel paradox. And just try telling Aristotle that he was wrong. You can't measure a wheel with a ruler, and the tape measure won't be invented until the 19th century. But the paradox was solved even earlier, with the help of logic. After all, what is a circle? It's a polygon with an infinite number of sides. Let's test this paradox. But let's start with a simpler polygon, one with 6 sides. In exactly the same way, we take it and roll it along. It seems that the large wheel travels the same distance as the small one, but there's a catch, and to spot it, pay close attention to how exactly the small wheel moves. To make this clearer, let's coat both wheels with paint. We roll them again and see that the larger one leaves a continuous line, while the smaller one leaves a dashed line. In other words, it's cheating and makes a little jump after each movement. Now, let's take one step closer to a circle. Let's use octagonal wheels. We'll coat them with paint as well and roll them along. Look, the small wheel is still jumping, but this time the gaps are shorter. I can do this with a 10-sided, 20-sided, or any number of sided wheels. The more sides there are, the shorter the gaps become. And if you increase the number of sides to infinity, you get a circle. And the small circle cheats in exactly the same way, but does it so smoothly that you don't even notice. The jumps are so tiny that they hide within the layers of paint. So, the lines only look the same, but in reality one is solid and the other is dashed. Congratulations! We've just proven a kindergarten-level truth. Different wheels are different. By the way, it took scientists 2,000 years to figure this out. But mathematicians can still claim that the wheels are the same. And this is where we'll start the most interesting mathematical tricks. And for this, I'll need your full attention. Look, we take the same wheels, but this time we don't roll them anywhere. Instead, we draw a line from the center right to the very edge. Of course, it will cross both wheels. Let's draw another line. Again, it's the same thing. And then again and again, continuing like this to infinity. Since absolutely all the lines have crossed both wheels, the number of points in each is the same. You might say that there's still space left in the larger circle, but not in the smaller one. All right, let's put a point in the large circle, draw a line to the small one, and you'll see that a new point automatically appears in the small circle. So, the number of points in the wheels, whether in the large or the small one, will always be the same. And here the universal rule of mathematics comes into play. If two things have the same number of elements, then those things are the same size. Only, in mathematical terms, this size is called cardinality. So, what does this mean? All this time, the wheels have been both the same and different. Yes, it's just that in one case we're talking about length, and in the other about the number of points on the surface. And by that logic, it's not just the wheels that are the same, but us as well. Let's put myself next to someone shorter. We draw one line through the navel, another through the crown of the head, and a third through the heels. For every point on me, there is exactly the same point on the shorter person. No matter which point we choose, it will have a pair. So, from the point of view of cardinality, we are the same, or have equal cardinality. Do you see where I'm going with this? By the same logic, I can now seriously claim 1 centimeter is equal to 1 meter. Yes, they differ in length, but they have the same number of points. They have equal cardinalities. In this way, infinities allow us to compare things that, in everyday life, you wouldn't even think to compare, because the answer seems obvious. And this brings us back to Hilbert's hotel. We managed to move an infinite number of old guests into just the even-numbered rooms and fill the odd-numbered rooms with an infinity of new guests. It seems impossible, because there are half as many even numbers as there are natural numbers. But let's compare them in the same way we compared heights and wheels. The first number is paired with the second with the fourth, the third with the sixth. Every number has its own even pair. So, there are just as many natural numbers as there are even numbers. There are infinitely many of both. And these infinities are the same size. They have equal cardinalities because they are the same type of infinity, countable. That is, the kind you can literally count 1, 2, 3, and so on to infinity. These are countable infinities. What's that? Are there other kinds? Of course. Remember how we couldn't accommodate an infinite number of people with infinite names in the hotel? Yes. That's because it was a completely different kind of infinity and countable. Yes, I can feel your brains boiling. So I'll demonstrate this kind of infinity with a completely different example. Right now, look at this sky. How many points are there in it? Yes, not stars, but actual points. Well, here's the first one. Let's say, here's the second, the third, and you can make a spiral like that. Is that all? No, because if you zoom in, you'll see there's still loads of space between the turns of the spiral that we haven't counted. Do you want to count that as well? I'll zoom in again. You can keep zooming in forever, which means you'll never be able to count all these points. This is what uncountable infinities are, tiny infinities that hide in the gaps and spaces of another infinity. To understand why uncountable infinities are always greater than countable ones, try counting the numbers between 0 and 1. The first one is obvious, 0. But what would be the second one? Maybe 0.001 or 0.000001? What about a number like this, starting from 0? No matter what number you name, I can add another 0, and my number will be even closer to 0 than yours. And so on, endlessly. It's like Bitcoin, which can be divided into very tiny fractions, infinitesimally small. You can send 0.0001 or even 0.0000000001. But while Bitcoin has technical limitations, in the world of mathematics there are absolutely no limits. That's why science still doesn't know what comes after 0, and never will. Moreover, the number of natural numbers like 1, 2, 3, and so on to infinity is actually less than the number of numbers hidden between 0 and 1, because we don't even know how to count them. It's like the number of points in a person's height, or the points on a wheel. There are infinitely many of them, and they are infinitely close together. It's a bit like a parable. You know, the one about the wise man who says that a tiny seed holds more within it than the whole world. The only difference is that mathematicians have actually managed to prove it. That's why Hilbert came up with Hilbert's infinite hotel. You'll be surprised to learn how many things we first discovered in our minds through mathematics, and only later found in reality, from the tiniest particles, which were first born in equations and only then detected in the collider, to the most massive and dense objects in the universe. It is within them that the last, third type of infinity hides, the one I mentioned at the beginning, and the only one that exists in our physical world. Have you already guessed what I'm talking about? It's time to answer the main question of this episode. Why are black holes the physical embodiment of infinity? What is infinite about them? The mass. The mass is colossal, but still finite. For example, the black hole at the center of our galaxy has a mass equivalent to 4 million suns. Perhaps, then, it's the speed at which everything is pulled into a black hole? No, because nothing is faster than the speed of light. And that, too, is finite. So, could it be the lifespan of a black hole? It's true, they live so long that no matter how long humanity lasts, we will never witness the death of a single one. Our universe has existed for almost 14 billion years, yet even the smallest black hole lives 10 to the power of 50 times longer. That is unimaginably long, yes, but still not infinitely long. So where, then, is the infinity in a black hole? Right at the center. There, the density and gravity are infinite, so strong that not even light can escape. Here is the first photo of a black hole, and it only appeared in 2018. But how do you explain that 4 years earlier, in Interstellar, the black hole was shown exactly the same? And it's all thanks to an equation that links matter and gravity. By looking at it, scientists were able to predict what black holes would look like 100 years ago. And this equation was derived by Einstein and that very same Hilbert, who founded this hotel. Here is the equation. Take any part of the universe. The right side of the equation tells us this is how much matter is in that part. And the left side says, right, so this is how it pulls you towards itself. This works for absolutely any place in the universe. If you put a large enough mass in one spot, a planet will form, which will attract a couple of satellites. Add even more mass, and the planet will turn into a star. Its gravity will be strong enough to make other planets orbit around it. But you can take a different approach. Instead of adding more mass, you can compress the mass you already have. What if we were to compress our planet down to the size of a golf ball? You would get a black hole. According to Einstein's equation, any object can be compressed so much that gravity itself will collapse it into a microscopic point. In other words, it would sort of collapse in on itself. This would create a real puncture in space-time. An infinitely small volume with infinitely high density at this point, and gravity so strong that not even light can escape. Scientifically, this puncture is called a singularity. It is, in fact, infinity within our physical world. Such infinities are called actual infinities, meaning they literally exist. Let's say straight away, this term isn't used very often in science, but it does describe very well what happens in black holes. And what I especially like is that, thanks to mathematics and infinities, we can imagine what the most beautiful, yet absolutely deadly, spectacle would look like: a person falling into a black hole. Presenting for your attention, a person falling into a black hole. The show, I am a black hole, and you're so you're approaching the black hole. Even as you get close, gravity twists not only the passing rocks, but even light itself. At some point, light will start to orbit in circles, and the world will turn into a complete optical illusion. You'll see your own back, because the light from it will make a full loop and reach your eyes. The world has already become strange, and we haven't even entered the black hole itself yet. So, where is its official boundary? Further in. And it's called the event horizon. Yes, because events that happen beyond the horizon never escape to the outside. In other words, they don't enter our world. Not even light can escape. That's why, starting from the event horizon, a black hole truly becomes black. What awaits you beyond the horizon? Well, it depends on whether you fall into an ordinary black hole or a supermassive one. Which one shall we start with? Let's start with an ordinary one. In it, gravity will increase so sharply that your feet will be pulled much more strongly than your head, and your whole body will be stretched into endless spaghetti. This is no joke. In fact, there's a scientific term for it, spaghettification. You might ask, but what if I don't want to become spaghetti? Is there any way to avoid spaghettification? Yes. To do this, you need to fall into a black hole at least 1,000,000 times bigger than the Sun. Then its gravity will be distributed evenly across your body, and without even noticing, you'll cross the event horizon. And after that, you'll freeze. For people on Earth, your time will come to a halt. That's why black holes used to be called frozen stars. Scientists have never seen them in real life, but from the equations, they realized that time stands still inside them. But what would you yourself feel at that moment? It seems like it should be the other way round. Time should speed up, and you would see the future. Remember the scene from Interstellar, where the characters ended up on a planet next to a black hole? 1 hour there was equal to 7 years on Earth. Well, inside the black hole itself, this effect is pushed to the maximum. But to notice it, you would have to slow your fall down significantly. Then light, and therefore information, would rush past you at tremendous speed. It would be like standing still in the middle of a huge crowd. But how could you do that if the singularity is pulling you in with such immense force? To slow down even a little, you would need about 1 billion rocket engines like those from SpaceX. Then you would have at least a couple of seconds, yes, they would appear to catch even the slightest glimpse of the future. Of course, you wouldn't be able to tell anyone about it, because even the little recording you might make for your relatives would also fall into the singularity and remain there forever, just like you. But what if we go even further and find out what happens next? It doesn't matter what particles you were made of before that. In the singularity, they will break down into even smaller parts and become part of a faceless, superdense mass. You will become part of the only physical infinity we know of. Yes. After all, apart from black holes, we haven't found any other infinities. Do you think the universe itself is infinite? No, scientists don't have a single piece of evidence for that. That's because we see and learn information through light. And beyond the boundary of the observable universe, there is no light. So, we can't find out anything about the universe on the other side. It's not the universe that's infinite, but only its tiny fragments inside black holes. And consider this, we've not only never been inside a black hole, we've never even flown close to one. But even so, we still know in detail what would happen to you at every stage on the way to the singularity. Once, Aristotle puzzled people with the paradox of the wheel. 2,000 years later, Hilbert came up with the trick of the infinite hotel. All of these are vivid images they used to try to describe something that's almost impossible to imagine, the concept of infinity. And thanks to the Einstein-Hilbert equation, we were able to calculate what infinity looks like in our physical world long before the first photograph of a black hole. So if anyone ever asks you why mathematics is needed, show them this episode. Mathematics is the language our universe speaks. First, we discover unimaginable concepts in our minds, and only then do we find their physical application. Black holes are just one of the consequences of Einstein's equation. Alongside them, scientists also predicted their complete opposites, white holes, which, on the contrary, expel everything from themselves. So far, we have no evidence of their existence. But it was the same with black holes, after all. Would you like to find out where else logical puzzles and all these mind games might lead us? Keep asking questions. And my shift has come to an end.